is Reinier Torenbeek. I am a systems architect with real-time innovations, and I will take some time to walk you through this RTI eLearning module. I will explain the fundamental principles of the Data Distribution Service for Real-Time Systems, or DDS for short. Right from its conception, the goal of DDS was to provide system developers an infrastructure that helps to meet a rich set of requirements common to many mission-critical systems. I will guide you through the basic assumptions underlying the concept of DDS and how they result in a data-centric infrastructure. You will learn that the DDS concept in itself is simple but powerful, resulting in systems that consist of many small, decoupled applications that require virtually zero configuration and that allow for highly customizable behavior. Systems that DDS was designed for and is used for typically have similar functional and non-functional requirements that are hard to meet. The goal of DDS is to help systems designers and developers with that task. I will mention the most important requirements. One is that DDS middleware shall promote predictable behavior and behave predictably itself. It shall provide means to achieve a high degree of fault tolerance. These systems are typically built to last for decades, so cost-efficient maintenance is important, as well as being prepared for future evolutions of the system. Often these systems consist of many processes and nodes, so the infrastructure shall scale accordingly. Another important issue is the complexity of these kinds of systems, which can be reduced by using DDS. All of this needs to be achieved under stringent performance requirements and typically in hybrid environments. In this context, hybrid can mean different programming languages, operating systems and hardware, as well as networking topologies. These are many and diverse requirements, and DDS will not magically meet all of these for you. However, it will provide you with an infrastructure that encourages you to take the right approach, and the meaning of right here is based on many years of experience in building such systems. This is achieved by two main principles. First of all, DDS encourages you to build your system out of components that are decoupled, both in space and in time. Components are decoupled in space if they can interact with each other without having to be aware of their actual locations. Indeed, at the application level, DDS components do not know where their counterparts reside. Components are decoupled in time if their interactions do not rely on a particular sequence in time. In practice, this means that they will communicate asynchronously. I think it is safe to say, in the DDS context, that component decoupling is the holy grail of system development. At the same time, related to this, the DDS approach discourages the sharing of knowledge between components. Examples of concepts that should remain local to each component are the algorithms it uses, its programming language, operating system, platform, etc. Ultimately, each component should be concerned about its own responsibilities only, resulting in maximum separation of concerns. That sounds nice and sort of obvious, but it is clear that we have to share some knowledge between components. Otherwise, they will not be able to work together. So the remaining question now is, what knowledge do we share between components? Again, from experience, we know that ideally, the knowledge that we share should be a stable aspect of the system. The less fluctuations or changes in our shared knowledge, the better. For systems targeted by DDS, this stable aspect of the system is typically the information model. Indeed, when developing a DDS component, the information model technically is the only aspect of the system that needs to be known. Let's zoom in on the meaning of the concept information model. Essentially, the information model consists of two components. The first is the data model, the second is the data interpretation. Starting with the data model, this defines the structure of the raw data as it is communicated between components. This part is actually explicitly shared between components as part of the development process, and defining the data model is an important aspect of DDS systems design. Analogous to languages, the data model can be considered the syntax of the information model. The second aspect is the interpretation of the data, giving meaning to the raw data. With DDS, this data interpretation is a form of knowledge that is not explicitly shared between components. Instead, it is part of the application logics. It can be considered the semantics of the information model. Since DDS revolves around the data model, I will spend a few more slides on that. The explicit sharing of the data model that I mentioned previously essentially means that DDS components interact via a strong typed data space containing structured data items. These data items represent the state of so-called observable items. In DDS terminology, these are called instances. Each of these instances has its own lifecycle of creation, updating, and deletion, and components interacting with the data space can manage the states of these instances or observe changes to the states of the instances. The data model itself, defining the structure of the data items, has to be defined in upfront by means of a programming language neutral definition language. This is typically a subset of the OMG Interface Definition Language, or IDL for short. Here's an example of IDL definition of a data item representing a fuel gauge of a vehicle. It is straightforward, a structure with several attributes of basic types. Note the // @key annotation, though, behind the attribute called VIN, the Vehicle Identification Number. The key annotation identifies that the VIN attribute uniquely identifies a fuel gauge among all present fuel gauges in the data space. This allows for simultaneously maintaining the state of multiple fuel gauges. And this is analogous to the way that a traditional database table can contain many rows identified by unique key values. The key definition is part of the data model. In order to be able to work with this fuel gauge data type, it needs to be translated into a set of language-specific types and functions to be used by the application developer. For example, if you are programming in C, the fuel gauge data type will look like this. The definition is generated by a code generator provided by the infrastructure. Not only does that generate the language-specific data types, but additionally it creates a set of strong typed functions or methods that allow the programmer to work with the data space in a type-safe way, with all the associated benefits of strong typed coding. Of course, this holds for any supported programming language, not just C, but also C++, Java, C#, to name just a few. For each of these, the mapping takes place according to standardized IDL to language mapping rules. Now that we know how the structures of data items in the data space are defined, we will take a look at how applications interact with the data space. Well, the updating and observing of the data space is done via the so-called publish-subscribe paradigm. It relies on applications declaring their intent to update particular items in the data space. These applications are the publishers, and on applications expressing their interest in updates of particular items in the data space. These applications are the subscribers. This declaration of intent typically, but not necessarily, happens at startup of each application via well-defined standardized API calls. Based on these declarations, the infrastructure is capable of creating efficient communication paths from the publishers to the subscribers for the relevant data items. Whenever a publisher updates a data item, that update gets communicated along the appropriate ways to any present subscribers, for example via multicast, unicast, or shared memory, but other transport mechanisms are possible as well. Typically, but not necessarily, this happens as soon as possible. The model is a so-called push model and each subscriber receives its own local copy of the data pushed out by the publisher. It is important to understand that all of this happens under the hood, inside the infrastructure. At the application level, publishers and subscribers do not know about each other, which is exactly what we want in the light of decoupling. Let's take a look at a simple animation illustrating this. The example is about the fuel gauge again. We see one publisher updating the state of the gauge periodically, and two subscribers receiving the updates via the communication path set by the middleware. The data gets pushed out from the publisher to the subscribers. It's all rather straightforward. A nice property of this paradigm, as used for DDS, is the possibility to have applications join and leave the backbone on the fly. The infrastructure takes the responsibility to detect and discover changes in topology. It will adapt its communications accordingly. This all happens without the need of configuration changes or centralized services. In fact, the RTI Connext implementation of DDS is fully distributed, which is perfectly in line with our goals and the DDS specification itself. This simple animation illustrates what could happen in a system where a publisher joins the system on the fly and the communication paths are updated dynamically. The pub/sub paradigm is common. It is the basis for several other communication infrastructures as well. However, the DDS approach to pub/sub has several appealing properties that make it a unique technology. We have already seen the fact that the data space is strongly typed. This can only be achieved by virtue of the infrastructure knowing the exact structure of the data items, the values of their attributes, and the key values that identify different data items. For short, the infrastructure is content aware. As a consequence, application complexity will decrease. Because of its content awareness, the middleware is able to take care of the lifecycle management administration of its items, but also can it provide advanced functionality like filtering of data based on its contents and a SQL-like querying for present data. Here is another animation illustrating how this works in practice. The subscriber on the top has expressed its interest in fuel gauges, but only those that have a particular VIN. The infrastructure will set up the communication paths accordingly, and as a consequence, updates for the lower fuel gauge will never be delivered to the subscriber on the top. Another aspect that makes DDS a special pub/sub technology is its support for a rich set of so-called quality of service settings. This means that the infrastructure is capable of treating different data items differently. Applications can choose from a rich set of quality of service attributes and attach it to the data in order to select the right behavior. The middleware takes care of the rest. Again, the complexity of the application decreases because the infrastructure takes more responsibilities. An example of a QoS setting is durability, which is about availability of the state of data items to subscribers. By default, its policy is of the kind volatile, which means that updates to data items will only be delivered to subscribers that are present at the moment of updating. However, if non-volatile kinds like transient or persistent are used, then the infrastructure will keep the state of those data items available to any late joining subscribers. This kind of QoS setting delivers ultimate decoupling in time, and remember, decoupling was the holy grail of the system design in the context of DDS. This animation shows the concept. If marked with non-volatile QoS, an update to the state of the fuel gauge is communicated to any present subscriber at the moment of publication. However, a late joining subscriber will receive the latest update as well, automatically, and without any burden to the programmer. This pattern is very common for our targeted systems. I have not yet explained anything in detail about the actual interaction of the applications with the data space, the updating and observing of the data items. DDS provides a rich API for this, especially on the subscriber side. For now, I will limit myself to the most basic aspects only. First of all, publishing applications are responsible for modifying the state of data items, or instances in DDS slang, in the data space. This includes the creation and destruction of instances, as well as changes to the values of its attributes. The amount of instances simultaneously present in the system can be pretty large. A number of hundreds of thousands is not uncommon. It is the publisher that indicates what quality of service settings are to be used while communicating the updates. Observing the updates happens on the subscriber side, where the application can be notified of changes in the state and lifecycle of the instances, and it has the possibility to query the current state of instances. For this purpose, several interaction patterns with the data space are supported, each with their own characteristics. Applications can poll for the latest state of instances by periodically accessing the data space. Polling is typically used for GUI applications, or for processes that run in periodic cycles. The second pattern is the listener pattern. It is basically a variant of the observer pattern. When using listeners, the middleware invokes user-installed callback functions as soon as changes in the data space are detected. The application can then process these updates. The third approach, called the wait set, is similar to the traditional socket select method. With this approach, an application thread blocks until a change in the data space is detected or until a timeout occurs. After unblocking, the application can access the data space and process the changes. In a sense, this is a highly responsive version of the polling mechanism. It is important to realize that whichever pattern is used, the subscriber will always have local copies of the data at its disposal. This is in line with the fact that subscribers do not modify the data space in any way. They truly only observe it. Consequently, different subscribers do not interfere with each other either. More experienced users at some point will notice the power of DDS when they start combining features to design reusable architectural patterns, like building blocks for your system. These patterns do not appear in the DDS specification and are built using the DDS API. RTI Connext DDS provides several extra APIs that do this for you, or you can implement your own customized patterns. Examples of such patterns are automatic component relocation, for example because of a crashed machine. Another one related to that is restoration of the state of a component after it has crashed. I will illustrate that by an animation. Here we see an application responsible for publishing the state of, again, a fuel gauge. This application is both a publisher and a subscriber of the fuel gauge. Now the fuel gauge is published with a non-volatile durability kind called transient. This means that the infrastructure will maintain the current state of the fuel gauge, even if the originating process for some reason, maybe a crash, goes away. If that application is now restarted, then, by virtue of the transient nature of the data and the fact that the application subscribes to the fuel gauge data, it will have restored its state immediately and it can continue where it left off. Essentially, this pattern is about replicating the state of a component inside the middleware, and as such, it is implementing a cold standby mechanism. Well, that concludes my overview of the fundamental principles of DDS. The only thing I would like to do is a concluding check to verify that DDS indeed helps meeting those requirements that I presented at the beginning of the presentation. Summarizing, DDS provides a fully distributed architecture, improving scalability characteristics, decreasing the risk of fault propagation, and it does that with components decoupled in space and time. which allows for flexible deployment, increases predictability of each component, decreases overall complexity, and promotes component reuse. These components are communicating with each other directly, improving performance, and via a strongly typed global data model, which ensures compile time type checking, allows for offloading complexity from the applications to the middleware, which allows for multi-site system development, and which promotes managed evolution. It does that using simple standardized APIs, leading to a flat learning curve and avoiding vendor lock-in. And these APIs are available in multiple languages, operating systems, and hardware, allowing for hybrid environments and ensuring product continuity. Thank you for taking the time to watch this video. If you have any questions, please feel free to contact me at reinier@rti.com.
Thank you for watching this portion of RTI's online training, focused on RTI Connext DDS. We'd also like to remind you that there are additional resources located on our eLearning webpage at www.rti.com/elearning. We also invite you to visit our community portal, where you can post general or training-related questions and receive answers to those questions. Lastly, please feel free to send an email with your questions or comments to eLearning@rti.com. Again, thank you for watching and have a great day.